Just one, yeah, one question is when you please feel free to interrupt during the lecture. It's entirely up to the lecturer how the lecturer will take care of the questions. So I think students should not worry about the time issue. But the only thing is that the audience in the Zoom couldn't hear the questions properly. So if you have a question, raise your hand, then we will try to deliver the microphone. Or if that doesn't happen, probably the lecturer can repeat the question and
Okay,
try to
yeah.
answer. Okay, yeah, great.
Okay, I'll try to remember to repeat the question. Good, is this thing is on? Okay, all right, so let's just pick up where we left off. So we were talking about some unsupervised machine learning tasks, and I was finished by saying that the loss functions for these are sometimes less than obvious. And so the next thing I want to talk about is what's the general principle we have for designing these loss functions. Okay. Okay, we saw in the case of the least squares fitting that it was sort of a natural thing to do. But actually, there's a general unifying principle which tells you in basically every case what the best loss function to use is. And this is sort of one of these deep statistical things. And it goes by the name of maximum likelihood estimation, or MLE. And it says that in general, the best in some precise statistics sense, like least biased, minimum variance, all these things, the best thing you can do is to maximize the likelihood of the data under the model. Okay, so it's sort of intuitively clear why that would be the best thing to do. Okay? And implicit in here, I would say, is a statement of what the model is. So the model is this likelihood. Okay, so the model you have of the data is a statistical model which posits what this likelihood is. And if you can then maximize this likelihood under the parameters of your model, this is the best loss function. Okay, so it's the least biased, the minimum variance, at least in the limit of infinite data. Okay, now I'm not a statistician, so I may be mangling some facts here, but this is my basic understanding of what's going on, is that when you have enough data, the maximum likelihood principle is the best way to go. Okay, and usually, as we said, the data is IID, right? So what this likelihood becomes is the product under the data in the individual likelihoods. And let's say the model is this theta, yeah? So it's just the product of each data point, its individual likelihood. Okay, and usually these products are not very numerically stable, right? So it's better to turn it into a sum, okay? So usually what we try to minimize, minimize the negative log likelihood, which is minus log of p, which is minus sum over the log of the individual p's for each data point. Okay? So that's the universal prescription for the loss function across basically every machine learning task. Okay? If you can identify what the likelihood the likelihood is you know the loss function. Okay, so let me give an example of this which will be immediately relevant for the first sort of application that we study, which is classification. Okay, so example, binary classification. Okay, so in this case, the way we'd like to think of our fitting function, okay, the way we'd like to remember, the fitting function is trying to map this to a label which is either 0 or 1, right? And so the way we are going to think about this problem, the model we have for the data, is that we give up, let's give up on trying to exactly get 0 or 1. Let's just say that the best we can do is get the probability that a given data point is background or signal. Okay, so we say that this is equal to the probability of X being class 1, let's say. Okay, so that's how we're going to interpret this, the output of our fitting function. Okay, and okay, so if F is the probability that X is class 1, then what is the, let's say my data has, what's the data? Let's say the data is X1 through X N1 is class 1, and X N plus 1 to, oh sorry, X N1 plus 1 and 1 plus N2 is class, oh sorry, let me do it this way. Let's say this is class 0, and this is class 1. Okay? So that's my data set. And so the probability, what's the probability of the data under the model? It's just, let me multiply the probabilities under class 1, which would be I equals N0 plus 1, N0 plus N1, F xi, right? And then what's the probability under class 0? So 1 to N0 is 1 minus f of xi. So that's the probability of the data given my model for the individual probabilities of being class 1. Yeah? So I'm using here the fact that the probabilities have to sum to 1. So either it's class 1 or it's class 0. Yeah? So of all the guys that are class 0, I should include this probability that is class 0. And then of all the guys that are class 1, I should multiply by the probability that's class 1. Okay. Good. So now I can just take the log of this. So my negative log likelihood minus log p, it looks like this. Let me just write it with a shorthand here. F of xi theta minus class 0 log 1 minus f. Okay. And I can do one more thing to write this more compactly. Okay. So I can do one more thing to write this more compactly if I put in the labels, right? So for all of these guys, the label is 1. For all of these guys, the label is 0. So I could write this instead as a sum over all the data. So L equals I over all the data if I just sprinkle in the right factors of the label. and there's a minus sign here. Okay, so whenever the label is 1, I pick up this term. That's that. Whenever the label is 0, I pick up this term, which is that. Okay? So what I've just derived now using the maximum likelihood principle is the loss term that we actually use for binary classification, which has a name. It's called binary cross entropy. And this is the loss for binary classification. Okay? And if you want, as a homework exercise, derive the analogous loss for multiple, so more than 2 classes, for greater than 2 classes. Okay? Which goes by the name of categorical cross entropy. Okay, so when we do top tagging, we're going to be using this loss and not the mean squared error loss. Okay? Another homework would be show that MSE is not the best loss in some example. Okay, any questions about that derivation? Yeah.
Maybe you can explain, you can define what do you mean by the best?
Right, so, okay, so I could, the question was maybe I can say more about what we mean by best. So, yeah, so the idea is, well, I would say, yeah, what we mean by best is that in terms of these, and so it's going to give you, well, it's going to give you in the limit of, say, finite data but large amount of data, it's going to give you the closest to the optimal answer. I think that's how I would say best. So in the limit of infinite data, I think probably all these approaches, including MSE, also give you the optimal answer, I think. First, I haven't told you what the optimal answer is. So let me answer your question by telling you the next thing I want to tell you, which is what is the optimal classifier? Okay. So, so what is the optimal classifier? So after I answer this question, I'll be able to answer the question you asked, which is what do we mean by best? Okay. So the optimal classifier, we can get this from the binary cross entropy if we view it not as a discrete sum, but as an integral. Okay, so what do I mean by that? How do I view this as an integral? Okay, so this is another little tidbit of statistics. Okay, whenever we have a sum over the data, okay, there's a continuum limit of that, which is an integral. Let's say sum over x. It's the same as an integral over the space that the data lives in, weighted by the probability density of the data. Okay, so this is a important continuum limit sort of thing to keep in mind. Okay? And we say that this is the sampling estimate of this. Okay, so this is called the sampling estimate. Of this. Okay, so yeah, I guess technically it should be like weighted by 1 over n data or something like that. Yeah, then this is correct. Okay, so good. So let's view this as the sampling estimate of some continuum thing. Okay, and we can view it. We can get it the following way. So L is equal to an integral. So we have the sum over the data, right? So we can integrate over the probability density for class 1. Yeah, for class 1. And that's the first term. And then we can also integrate over the probability for class 0, probability density for class 0, and that's the second term. Does everyone see how I got from there to there? So actually, it's probably easier to see. It's probably easier to see it from this form of it here. Okay. So here I'm summing over all the data from class 1. That data has some probability density, which I'm calling P1. Okay. And here I'm summing over all the data from class 0, and that has some probability density P, I'm calling P0. So I'm basically using this relation twice. Okay, I'm using it once here, and I'm using it once here. Okay? So now I want to minimize this with respect to theta. And so I can use my usual calculus of variations. There's no derivative terms here, so I don't need Euler-Lagrange. I just take a derivative of this with respect to f, basically. Okay? So I set to 0 the variation with respect to theta, which amounts to saying that P1 of x over f minus P0 of x over 1 minus f, that has to be set to 0. Okay? And now I can solve for f very easily. And so f, so basically I put a hat to indicate that's the optimum, okay, that's the best fit solution to this, is equal to P1 of x over P0 of x plus P1 of x. Okay, which I can write in terms of something called the likelihood ratio. Okay, so the likelihood ratio is defined to be P1 of x over P0 of x. Okay. So that's the optimal classifier. Okay? And it's basically, so let me make a plot of this as a function of R of x. Okay? So the optimal classifier, if the likelihood ratio here is between two positive quantities. Okay? So it can go from 0 to infinity. Yeah? So at 0, f is just 0, right? And as r goes to infinity, this becomes 1. So it just looks like something like this. And in fact, what we say is that f is monotonic with r. Okay, so the classifier output is monotonic with the likelihood ratio. So if we're interested in all the events that have probability greater than something of being class 1, how do we get that? We get that by saying f is greater than some cut, right? And that is equivalent, because of this monotonicity, with this being greater than some cut. Okay, so a cut on f translates to some cut on r, 1 to 1. Okay? And so what we've just derived, so basically, let me say it in words, the optimal classifier is the likelihood ratio. And this has a famous name in statistics. This is called the Neyman-Pearson lemma. Okay, I think it dates back to 1930 something, 1934 maybe? I don't know. In the 30s. It's very old result. And they phrased it not in terms of classifiers, but in terms of hypothesis tests and what they call a simple hypothesis test. But in the current modern ML language, we would say it's a classifier. Okay. So if you have the likelihood ratio between class 1 and class 2, you have the optimal classifier. And so going back to your question, I would say the best loss term is the one that lets you approach this likelihood ratio answer the quickest as your data increases. That's how I would see it. Everything else will also eventually reach this point, but it may reach it slower. Yeah. Okay. I think, have I lost everyone? Maybe people want to ask a question or two? Is clear? Yeah.
Is the PY on the right equation?
Do I want to consider what on the right equation?
The probability for Y?
Where's y in the right equation?
Well, I think you, the
Here?
label, yeah, here.
Yeah.
Yeah. PY, P1X, and PY, P0X, I think that's correct.
Py. What's py? There's no py.
Because PX on the left, that is going to be not just P1 plus P0, but that should be Py equals 1, P1 plus Py equals 0, P0.
That's indicated here. Yeah. So the question is, where did the label go for the people on Zoom? I guess. Yeah.
Okay.
Is that where does the label go? The label. Y is the label.
Yeah. Y is the
Yeah.
label.
Yeah. So what happened to the label?
Yeah, that's right.
Yeah. So basically, these two terms here are exactly those two terms up there. So one term has the label y, and the other term has the label 1 minus y. The y is just 0 or 1. So when I plug in 0 or 1, I get these two terms exactly. Yeah. So there's no py involved. Yeah. Maybe it would help if I just drew a picture. So let's say my data is two-dimensional. Okay. Maybe I'll use some colored chalk. Okay. Well, they have colored Hagoromo? I didn't know that. Okay, so let's say this is class 0, and let's say this is class 1. And it's important, that they overlap with each other. Okay, so that they're not completely separable, right? And so what I'm talking about is, so this scatter of points here is described by some probability density P0 of x, okay? And this scatter of points here is described by some other probability P1 of x. And the ratio between these two gives you the optimal classifier, the best way to tell these two apart. The most powerful test. Does that make sense? So when these two densities are the same, like really the same, you can't tell, right? When one of them is 0, let's say over here, right? When one of them is 0, then my classifier is going to say it's definitely class 1, right? P1 over P0 is infinite, definitely class 1. And when when 1 is 0, like over here, the likelihood ratio will be 0. So the probability that it's class 1 is, you're sure that it's not class 1. Okay? Okay, good. All right, that's how we get loss functions, and that's the binary cross entropy. Now I think we're ready to introduce neural networks. Okay, so yes.
So here, this function f looks very similar to me like a sigmoid.
Yes.
So is there any connection between this f and the sigmoid?
This f in sigmoid, well.
Or you can find some connection when some condition is satisfied and you can go to sigmoid, for example.
Yeah, I think the only connection comes to mind immediately would be that, okay, the question was, this looks like a sigmoid activation, which I'm going to introduce in a moment. But is there any connection more directly with sig? I mean, I think, you know, sigmoid is a transformation between, first of all, this is not the sigmoid. So the sigmoid goes to minus infinity. Yeah, so it's not really the sigmoid, yeah. Yeah, so this is just a map from the half infinite line to probability space. Sigmoid is, if you think about it, is a map from the infinite line to probability space. So they play a similar role, probably like 0 to 1. So the infinite line to an interval.
But another question.
Yeah.
How if I have multiple?
And it's monotonic, as the sigmoid is. So I think based on those two properties, maybe it's,
Also here you
Well,
have just
okay.
0 and 1 for the label y. What if I have more labels, like n labels?
right. Well, that's homework problem number 1.
Homework problem.
Yes. You're trying to get me to say the answer to the homework problem. Yeah. Okay, good, yeah. So trying to repeat this all for the multi-class case is an interesting, straightforward exercise based on what I've said. Okay, good. So now we've talked about what the loss function is, what are some common ML tasks. Now it's time to specify what the fitting functions are, okay? And so this is where the modern technology, GPUs, and all this stuff comes in. This is where neural networks come in. Okay, so the family of fitting functions so that's what neural networks give us, okay? They give us extremely, so that's all neural networks are. You should think of them as a way of parametrizing, a very flexible and expressive way of parametrizing a general family of fitting functions that's so flexible and expressive that it appears to be applicable to basically any task we can come up with, okay? So if you like, you can think of a neural network as, more abstractly maybe, like there's some, like mathematicians will study functions on a function space, right? With maybe like L2 norm, blah, 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 right? So integrable functions or something. So functions on a function space. Neural networks are almost like the CS person's answer to how do I parameterize the space of all functions. Yeah. So neural networks are extremely expressive, meaning they can fit basically anything. They scale well to very high dimensions. Okay, and that's a statement of they have a special recursive structure that allow their derivatives to be calculated very efficiently, people realized. And under the hood, they're just repeated matrix multiplications. And people realized that that's perfectly suited for this thing called a GPU. Okay, so a number of random things had to come together for this statement to be true. Okay, they scale extremely well computationally to high dimensions. And I would say, actually this is something which people actively study, but they generalize, I would say, unreasonably well beyond the training data. I'll explain what this means maybe more in a moment. As in, they are unreasonably robust against a phenomenon in machine learning in general called overfitting. Okay, they're way more robust than you would expect. As in, you can have a situation where the neural network has more parameters than there are data, which classically would lead to severe overfitting, but the neural networks don't seem to do that. And I would say the CS people don't even completely understand why this is. That's something they still write papers about. Okay. All right, so let me now, did I mention? Oh yes, okay. So, good, so I'm not gonna have time to prove this given the time constraints, but one thing which you should probably know that exists in the in this, when I say that they're extremely expressive, is something called the universal approximation theorem. Okay, and this was originally proven for a single layer but infinitely wide neural network, and later proven for a fixed width neural network that's infinitely deep. But basically, the flavor is that a large enough neural network can, at least theoretically, fit anything. Okay, I think you have to say some things about smoothness and yada yada. Okay, so a large enough neural network can, in principle, describe any function in any dimensions. Okay, and the kernel of this proof is basically with this, say, infinitely wide neural network. Let's just do the one-dimensional case. I'm not going to prove it, but the kernel of the proof is to show that you can fit this. Okay? So if you can get a neural network, show that your infinitely wide neural network can fit this window function exactly, then you can approximate any function in 1D with a sequence of these window functions, right? Yeah, you could just do this. Yeah, so you can approximate it with, you can break it up, like Newton's, what is it called, the Newton method or whatever, right? Or, yeah. So then yeah, so once you show that one neural network can do this, then you just put them all together to do this. Yeah. Okay, so that's the universal approximation theorem. And I guess people believe that is the underlying reason why neural networks are so powerful. Yeah. Okay, so what's the simplest neural network? Okay, I'm going to just outline what this is. And it's called a fully connected or feed-forward or dense neural network. And it's just one example. And in Gregor's lecture, I think his first lecture, you're going to describe a huge family of these things, going way beyond this. So this is the simplest one. Okay, and yeah, it has many names. Feed-forward, fully connected, dense neural network, okay? And so let me just draw it in the way you'll often see it represented, which is both a convenient way to visualize it and a reflection of the fact that I think most CS people don't know linear algebra. But let me explain what I mean. Hope there are no CS people in this audience. Okay, so this is how you'll normally see it. I am being recorded, that's true. I'll never get invited to NeurIPS now. Okay, good, so this is a graphical representation of a neural network, okay? And let me just explain whatever, and so we'll draw also connections between all these things. Okay, so let me just, so this is the input. These are called layers, okay? So these are called layers or hidden layers. Was there a question? What? No, okay. So hidden layers, okay? And the first layer here is the input layer, okay? And so this is the input data, x. Okay, so for every circle here, that's representing one of the features. Okay, so we just think of x as a big old column vector, right? So x1, x2, xd. Okay, and then we represent it like that in this picture. Okay, good. And then each one of these is a hidden layer, which I will denote like this. Okay, and then finally we have the output. This is what the function actually outputs. Okay? All right. And notice how the output could be a vector as well. All right, so we have the ability to make our neural network vector valued. if we want it to. Okay, so this could be a vector as well. And then finally, so what are all these lines here? So each line here is what we call a weight of the neural network. Okay, it's one of the parameters of the fitting function. So these are the weights. And the way we relate the weights, so notice how there's one weight for every connection, for every pair of, these are called nodes, by the way, nodes. So there's one weight for every pair of nodes in these adjacent layers. Okay, so the weights are a matrix, right? Yes, yes.
Network, this
Yes.
Node is scalar, right? Each node is scalar.
Each node is a scalar.
Yeah, yeah. And this the input is vector as a array of the node, right?
So the way you should think about it, at least partially, somewhat, is that each layer is like a vector, is like a column vector.
But my question is that can you have also like a vector, as a node? For the single node?
Not in this feed-forward neural network sense, no.
Is there any extension for that?
Yeah, I mean, sure. So what you would be describing is if each node was itself a vector, you could think of that, what we would say is flatten that to one big column vector, right?
Yes.
And then like each sub-vector that describes the node is like a chunk like this, right?
Yes.
And then you could restrict the weights in some way to respect that. So instead of, this is called fully connected because I connect every node with every node.
But what if I want to protect this
Yeah, so you could, if
array?
you want to protect that vector, you could somehow restrict the weights to not go between vectors or whatever. So you can study something that's not this fully connected thing and accomplish something that you have in mind, I think. Yeah. And then I guess other architectures like CNNs or RNNs, they also deal with this in other ways. Yeah. Good. Okay. So right. So the weights are just so the weights are a matrix, and they connect subsequent layers. And so you see the structure of this neural network is to propagate information this way. Yeah, that's why it's called a feed-forward neural network. Okay. And the way it propagates the information is just by matrix multiplication. So let me just write what the first layer looks like. So x1 is just the first weight matrix. That's this one here. That's W1. Matrix multiplying the input layer. Okay? And it's also a good idea to include what's called a bias. Okay? So these are weights, and these are biases. And that's generally because, as we'll see in a moment, the point 0 is a special point. And so we wanted the ability for the machine to force the output away from 0 if that's a good idea or not. Okay? So the biases are also parameters of the neural network. Okay. Now, if it was just this, okay, so now XL is WL x minus L minus 1. That would be the recursive or self-similar structure of a neural network. Each layer you get from the previous layer in the same way with its own set of weights. Okay. Now, if it was just this, though, my neural network would be trivial, right? If it was literally just this, what would happen? What would my function be? Anybody paying attention? If it was literally what I just wrote here, what would my function be? So Z is equal to W L plus 1, I guess, in my notation, XL. So what is Z as a function of X? If it was literally just what I wrote here. Yes, thank you. Somebody's paying attention. So Z would just be one big matrix multiplying X plus one big bias. Purely linear, right? So that surely can't fit everything. So that's not the whole story. So indeed, what we need in addition to this is what's called an nonlinear activation. We need a source of nonlinearity. Okay? And so what we do here is after every layer, we subject it to what's called a activation. Okay? And it's because of this activation, that's how neural networks, these kind of neural networks are able to fit everything. And let me just tell you an example of an activation in a moment. Let me now tell you an example of an activation. Okay, so you need a nonlinear activations to fit any function. Okay, and actually, in principle, it doesn't even matter too much what the activation is. Nevertheless, people, for practical reasons, have settled on like a particular best choice. But historically, I think neural networks started out with an activation that maybe was biologically inspired, but looked like this. Okay, maybe people studying real neurons found like the electrical signals look like this or something. So this is an example of a nonlinear activation function. And it's called this one, which is e to the x over 1 plus e to the x. This is called the sigmoid. Okay? And it maps x of minus infinity to 0 and x of plus infinity to 1. And it has this region here, you know, that's interesting. Okay? Closely related one to this is the tanh activation, which is just the sigmoid shifted down. So this is tanh. Is another example. Okay? Similar property, has an interesting region and regions where there's like no information. Yes, question.
Are there constraints on these activation functions? I'm just wondering if your statement that you can fit anything is really just a statement that you can choose any activation function, or if there's more.
I think, yeah, if I remember correctly. So the question is, what are the constraints on these activation functions to be able to fit anything? And I think the original proof, basically the original proof was probably for a particular choice of activations, like sigmoid. I think subsequent proofs have generalized it to basically any function that's non-polynomial, maybe? Is that the restriction? I think it can't be polynomial. There's some restriction, but otherwise it's almost anything goes.
I think in the original paper by the non-universal approximation theorem,
Yeah.
actually that was an example of the activation function.
Yeah.
But as you said, it does specify the properties. When
Maybe it
x
has to be
goes
monotonic.
Yeah, something like that. So
Monotonic and non-polynomial.
when x goes to infinity, it approaches a certain value.
Oh.
And x goes to minus infinity, it goes to another.
I'm not
thing.
sure that's even necessary. Yeah, so I think that even that's not necessary anymore. Yeah, maybe it just has to be non-polynomial, I think. Yeah. Don't quote me on that. I don't remember.
Oh.
Yeah.
Yeah, I was just curious because even if it is polynomial, if we allow it to be like quadratic polynomial, then
It is nonlinear, right? Yeah, yeah.
we can actually build any polynomial out of that.
But I think it's important to have it be, I don't remember, yeah. Maybe somebody can check on Wikipedia. Yeah, so anyway, it's almost anything with some restrictions. That's as far as I can remember for sure. Good. So actually people found that these were not good activation functions for practical reasons. And it's something having to do with the gradients of these things. So when x is too large or too small, or really anything other than the central region here, these activation functions, their derivatives go to 0 very quickly, right? And it turns out the derivatives, as we'll explain in a moment, the way these things are optimized or minimized, these neural networks, it's all about the derivatives of them. So once the derivative goes to 0, you sort of lose information. You can't update the weights anymore. So yeah, turns out these are not good. They're not what people use anymore. because of something called the vanishing gradient problem. And what people realized, and this was literally a breakthrough in modern machine learning, but people realized that they could get their neural networks. So yeah, so using sigmoid and tanh limited the depth that neural networks could go to. So this vanishing gradient problem gets worse and worse the deeper you go. And that was holding back AI for a long time until somebody had the bright idea that maybe we should just use this function. And I don't know how they figured this out, but yeah, so this function is called the rectified linear unit. And it's literally just x for x greater than 0, or 0 for x less than 0. So it has a vanishing gradient problem here, but somehow, I mean, it doesn't have it here, and that's enough to solve the problem. And then this allowed them to train neural networks much deeper. Basically, they could go as deep as they wanted. And that was a big breakthrough in performance. Yes, yes. So maybe that's useful. I mean, the neural network can turn things off. It can learn to ignore things if it wants, or it cannot. I mean, it can choose. So yeah. So this is the one. This is the activation that, or something like it, is the activation that everyone uses now. Okay. This is where the machine learning becomes like engineering or art and not so much science. But anyway, so this is just something that's good to know. Okay. Another comment is, this is also like not a very physicsy way to do it, but this activation, what does it even mean? So these are column vectors, right? So how can this activation, which is a scalar function, act on a column vector? So the way that it works in practice, I mean, it's just not very natural from like a linear algebra point of view, but it's fine for a computer, is these A's, we say that they act element-wise. So the A that acts on a column vector, so x1, xd, let's say, it just acts element by element. So that's what that means. Okay, and so with these you can define a fully connected neural network, which is the most basic neural network that you can work with, and actually is a pretty good building block for many other types of neural networks. So this is sort of the one to first get to know. Okay. All right, so if you take all the weights and all the biases together, these are the parameters of the neural network. And okay, and so just one more piece of terminology. So as you can see, to define a neural network, we have to make a bunch of choices, right? So nobody tells us ahead of time how many hidden layers to use, how many nodes in each hidden layer to use. I mean, in principle, you can choose your activation function. So all these things are what are called hyperparameters. Hyperparameters. So these are called the trainable parameters because these are the things that we're going to fit using the loss function. But the hyperparameters are things that we don't vary during the fitting process. Okay? And so, but still, we might want to, still the performance of our neural network, or how good of a fit we get, could depend on the hyperparameters. So the hyperparameters could be like L, the number of hidden layers, the number of nodes. So this is the number of layers, the number of nodes in each layer. And in particular, I mean, in principle, you don't even have to choose these to be the same. You could pick 100 nodes for the first layer, 200 nodes for the second layer, et cetera, right? There's the choice of activation. And the list goes on. Okay, so these are parameters that you might want, hold on. These are parameters you might want to also, in some sense, fit for, but you do this outside. First you fit for these things, for a given choice of hyperparameters, and then you might do a scan over these. As you can see, that starts to get expensive, right? But you might do a scan over these to see if there's some choice of hyperparameters that does a better job than others. Yes, question? So are there attempts to make the hyperparameters dynamical? As far as I know, it's not so straightforward. I'm not aware of any attempts. I mean, okay, there's literally tens of thousands of ML papers, so everything has been attempted. But you know, the basic problem is that, so using this construction, okay, using this construction here, I get a differentiable, like in a mathematical sense, a differentiable function of the weights and the biases. Like I can differentiate with respect to them, right? But these things, you know, how do I differentiate with respect to them? So, so making these dynamical is not so straightforward, I think. Yeah.
No, I was thinking because this would be the closest analog to functioning of the brain in a sense.
Mm. You mean because the brain can grow or something?
Well, yeah. You strengthen certain connections via.
Well, yeah, that's happening here, right? So these weights are like the connections between neurons, right? So this whole thing is like a brain, yeah. But like the brain can grow, like we can add and subtract neurons as we age or whatever, right? So that's like the hyperparameter scan maybe, yeah. Yeah. There are tools to scan over hyperparameters efficiently. So rather than lay down like a uniform grid or something, they're like Markov chain type things that try to scan over hyperparameters more efficiently. Yeah, but that's a whole other topic. Yeah. Good.
Maybe dropout is one of the
Dropout, yeah, you could say, yeah. So there's a thing that regularizes overfitting, which I'm not going to have time to get into much, but basically literally just deletes nodes at random. So yeah, if there's some like, if that converges to something, you could view that as, yeah. Mm-hmm. Okay, good. So, right, and so here you also see that the DNN is just matrix multiplication over and over again, okay? And this is why GPUs, so I think it's in the 2010s, that people realized that GPUs, which had been developed for totally other applications, right? So you can play Grand Theft Auto or whatever. So developed for like gaming, right? Or I don't know, making movies or something. But they were developed also to accelerate matrix multiplication. So GPUs are not general purpose computers, but they do one thing really fast, which is matrix multiplication. And so people realize, hey, if we could just figure out how to program a GPU, you know, to do neural networks, we might get a huge performance boost. And in fact, that's what happened. Okay? So that's why almost all this modern machine learning, you really need a GPU to do all this stuff. Because doing it on a CPU is just too slow. Okay, actually that brings me to my next point, which is also with this structure, we can see in a simple example how the number of parameters of a neural network can easily get very large. Okay, so let's just do a simple example. I mean, the basic reason is that the weights here go like the square, or the product, right, of these adjacent layers, right? And so, you know, let's just count the number of parameters that you might have. Let's say my input layer is 100-dimensional, although for an image you might have 1,000,000-dimensional, right? And let's say I keep that structure going for some number of layers, and then maybe I just output to one layer one node at the end. Okay, so each layer here is going to have how many weights, roughly? It's all the pairs of connections, right? So it's 100 times 100. So each layer is going to have 10 to the 4 parameters, plus the biases, right? And let's say I have a typical neural network that we might use in high-energy physics for some simple thing, might have 5 hidden layers, I don't know. So now we're at 50,000 parameters. So let's say this, suppose L is equal to 5, then now we're talking 5 times 10 to the 4 parameters, right? So just in this, so this is a very standard, small, neural network. You could train it on a off-the-shelf GPU in, I don't know, depends on how much data you have, but you could train it in, 10 minutes or something. Has 50,000 parameters, yeah? And you can easily get to millions this way, okay? So it's this large set of trainable parameters. That's where the special challenges of training fitting neural networks comes in, okay? So that's the computational challenge. So can easily get large number of parameters. And this is the computational challenge, is how to minimize a function of 1,000,000 parameters. Okay? So that's what I want to talk about next. I have to keep an eye on, when did I start? 1:30, right? Okay. All right, good. Any questions? I feel like people are more quiet after lunch. Yes, yes.
Even though it's not really related to the one you discussed right before,
Mm-hmm.
it's more about the one you dealt with like earlier today. So there you mentioned that, so even without LHC, if we can build one generative model, then we could think of replacing LHC with the generative model that we have built it. But then the question is, if the generative model was built out of the fitting function with parameters of number, for example, 1,000,000, then how can this model be different, and how can using this model can be different from using like one model defined with Lagrangian with like 1,000,000 operators in it?
I guess, okay, so, all right. So I think you're asking maybe, given, neural network that has potentially large number of parameters, how do we trust that it's extracting anything useful, predictive out of the data, and not, and so, okay, so I think that's a general question about overfitting or overparameterized models. Is that sort of the gist of it?
I think it is. Yeah, I think it is related.
Okay, so good. So I think, yeah, so let me discuss, so, well, one short answer is this generalization puzzle that I mentioned before, which is that neural networks seem to, in the limit of many, like large number of parameters, they seem to have some kind of collective phenomenon that's not fully understood, where it's almost like they have like collective emergent zero modes and things. So all their parameters don't act together, act independently anymore. So overfitting somehow gets smoothed out or regularized. The other thing is we can diagnose or test whether we're overfitting or not. So we can tell whether our neural network is overfitting or not. So that's the empirical or pragmatic approach, yeah. So we can diagnose or verify whether it's overfitting, and if it's not, then we should be able to use it, yeah. Okay, good. So the next thing I want to tell you about, in terms of the basics, is how do we train these neural networks. So training is what we call fitting. Okay, so fitting the neural networks to the data, we say that's training them. Okay, so how to fit with 10 to the 4 or 10 to the 6 or 10 to the 9 thetas to the data. Okay, so that is a computational challenge that has been basically solved. I don't have time to go into the nitty-gritty, and probably you wouldn't want me to either. So let me just try to sketch some of the basic concepts. Yeah, I won't have any time to describe, okay, yeah, so I won't have any time to describe one important thing, which is called backpropagation, but let me just mention that when I get to it. Okay, so in general, so we want to minimize some loss function, like the binary cross entropy. With respect to the parameters theta, right? So we want to minimize with respect to theta. And the first thing you might think of trying, right, is like let's say the function is this, right? And we want to identify this point. Okay, this is a way oversimplification for all sorts of reasons. There's a million-dimensional parameter space, and in general, these functions are not convex, right? So a better approximation to what's going on is like this, and then multiplied by a million dimensions, which I can't draw, right? So, okay, but let's say your function looked like this. How would you try to minimize this? The first thing you might try is what's called, I think it's called the Newton method. It's a second order method and involves basically taking a trial point, call that theta 0, right? And then expand around this to second order, right? So if your function were exactly quadratic, this would be exact. Otherwise, it gives you some approximation to what's going on. So you might say, let me approximate L with so let me say theta is equal to theta naught plus delta theta, right? And let me approximate this with, the Taylor expansion around theta naught, right? Like that, right? And then what can I do? I can, so this is just I can just truncate this to second order as an approximation, and I can just differentiate with respect to delta theta and solve, right? And so this will give me my next guess for the solution, right? So I can just differentiate this with respect to delta theta, solve it, and that will say that delta theta is equal to minus something like that, right? So that'll give me, so if my theta naught was here, maybe my delta theta puts me here. Okay, and then I can iterate. And then I'm going to get closer and closer to the solution. Okay? So I think this is called the Newton method, or Newton's method. And it's generally acknowledged that this would be the best approach if you could pull it off. But why does this not work for neural networks? Yes. So here I simplified things by assuming I was in one dimension. But what happens if I'm in a million dimensions? So this here becomes a big matrix, right, called the Hessian, I think. And then this is the inverse of that matrix, right? So inverting a million dimensional by million dimensional matrix is just still not computationally feasible, even with GPU, okay? So simply this will not work, okay? So this fails for neural networks because need to invert very large matrix. Okay, so instead, what people have come up with is a first order method that's not going to be as efficient as this, maybe, but also has its benefits, as we'll see. Okay, so instead what we need is a first order method. And so instead, a first order method, which is kind of, I think it's kind of stupid when you first hear about it. Like, how could this possibly work? And yet it does. So the idea is basically truncate to first order. And then, based on this example maybe, so at first order, what do we get if we just evaluate the derivative at theta naught? We get a vote, basically, in the direction that we should go. So it says, don't go this way because the derivative is pointing this way. That's the first order method. So you say, so the first order method is to hope that the gradient points in the right direction. And believe it or not, this works. So we just say that if you look at that, I guess it's got a minus sign in this example. Okay? You hope that the gradient at least points roughly in the right direction of where you should go. And then there's a choice to put a coefficient here. So this coefficient is an important hyperparameter, and it's called the learning rate. If you choose, because of course the derivative is never going to be pointed in exactly the right direction, so you don't want to be overconfident and choose the learning rate to be too large, because then you'll just end up totally in the wrong place, right? If you choose it too small, it'll take forever to reach the minimum. So there's some tuning of the learning rate that one usually has to do. But that's it. That's the idea of how these things are minimized. And this is called gradient descent. Okay, so any questions about that? Yeah. Yes, good. So that's the next thing I want to say. So let's suppose this is my loss function, okay? And let's suppose I start here. So where I start is always chosen randomly in these neural networks. Okay? The starting point is chosen randomly. And in fact, that's a big source of variation. Every time you train the neural network, you're going to get a different result, because where you start is random. And so usually what we do is we try to train many neural networks and ensemble, like average their predictions together, or we use the variance in the outcomes as an estimate of our uncertainty. But okay, so let's say I start somewhere random and I start over here, right? If I just use gradient descent, I'm going to stop once I get to a place where grad L is 0, right? And that could be a local minimum. So then I'll just stop, and then I don't have the best outcome, right? So that's the problem with this would be called vanilla gradient descent, okay? So that's the problem with this. And so you've really identified the next thing I'm going to say. So problem can get stuck in local minima. Okay. And so people have invented what we actually do to minimize these things is sort of motivated maybe by thermostatistical mechanics, I think. But it's to introduce some noise into the problem. So let's say I just do vanilla gradient descent and then I get stuck here. Well, if I can introduce like a temperature to the system somehow, then I might randomly jump out. So I might get stuck there for a while and then I randomly jump out. And then it's just like, so I'm like in a metastable state but there's some temperature, so I can randomly jump out. And once I jump out, then I can keep doing my gradient descent and end up where I'm supposed to be. So that's the idea of what's called stochastic gradient descent. And people realized, I guess, that there's a very simple way to introduce noise into this problem. A very effective and simple way to do that, okay, which I will now explain. Okay, so we need to get noisy gradients. So actually, it's a funny situation where, you know, the best estimate of the gradient is actually not as good as a worse estimate of the gradient, a noisy one. Okay, so solution to the problem of getting stuck in local minimum is introduce noisy, in the statistical sense, gradients. Okay, so remember this L here, let me bring this down. This L here is a sum over all the data. And that's like the best, cleanest, least noisy estimate of the gradient that you could get, right? So this gradient of L, we could view this as the average over the data of the gradient of the individual L's, right? Averaged over the data, right? So that's like the cleanest, least noisy estimate of the gradient you could get. And so what people realize is, hey, we can make this noisy by not taking the average or averaging over less data, right? Remember, so like, what is it? Basic statistics. The more data I average over, the smaller the variance is going to be, right? So I can make the variance bigger by averaging over less data. I could even take this to an extreme and calculate this gradient for an individual data point. A very noisy estimate, right? So stochastic gradient descent is to update the weights with respect to the gradient of L, let's say summed over a subset of the data. Let me just write it like this. Okay, does that make sense? So if I sum over all the data, that's regular gradient descent. Okay? And that'll get me stuck. If I only sum over a subset of the data, now I get a noisy estimate of the gradient. There's some built-in variance just from the variance of the data. Like I took a sample now of my whole data set. So I get a gradient which is not perfect. And that turns out to be enough to not get stuck in these local minima for the most part, empirically. Okay? And so this subset of the data that we compute the gradients over, this has a name. It's called a mini batch. Okay? And then the way we do these fits is, let's say this is all of our data. Okay? We will divide up all of the data into mini batches. So this is mini batch 1, mini batch 2, mini batch n, let's say. Okay, we'll divide it up into mini batches. Just for example, maybe my data has 1 million instances and my mini batch size is 100. That's a common choice. So I'll divide up my data into 10,000 mini batches, and I'll calculate the gradient over this mini batch, okay? And I'll update the weights, meaning I'll shift the weights by something. Now I'm at a new place in parameter space. And then I'll keep doing that over all the mini batches, okay, until I've looped over all the data. So my gradients have gotten jiggled around, my parameters have gotten pushed around, 10,000 times by the time I've looped over all the data, right, in this example. Okay, so, and looping through all the data is called an epoch, or training epoch. And to do one of these fits to the neural network, we would want to loop over the data in this way many times, maybe 10 times, 100 times. You'll see people do it thousands, tens of thousands of epochs. You'll train it until it's converged somewhere. Okay? So looping over all the data. That's an epoch. Okay? So that's the nuts and bolts of how you fit a neural network. After every epoch, it's conventional to shuffle the data so that the neural network doesn't see the same data in the same order over and over again. So after every epoch, we shuffle and repeat n times. That's how the neural network is trained. Okay, can I just take 2 more minutes? Okay. Any questions about that?
The number of local minima scale with the number of nodes and number of the layers.
The number of what?
The number of local minima.
The number of local minima, I don't know if there's any theorems about that. I've never seen any good analytics about that. Though people study it. For general fully connected neural network, I'm not aware of any parametrics or analytics about how many local minima there are. Yeah. Yeah.
So when you choose the subset data, like the size of the subset data patch, is it like chosen just by like experience, or is it chosen like a certain criteria, or is it really just independent on the size of the subset?
Good. So, I mean, okay, so this is another hyperparameter, the mini batch size, right? The learning rate is another hyperparameter. So I don't know why, but yeah, there are like best practices, choices that people make that seem to work broadly. And then, but sometimes we'll see like a larger mini batch size helps, and sometimes it doesn't, most of the times it doesn't help. And then the learning rates, they come with like default settings in a lot of these packages. So a lot of things are sort of chosen for you already and seem to work okay. Is there a general reason for that? Probably, but I'm not aware. Like that's something, there's a whole branch of like theoretical ML, people who study this sort of thing. But empirically, people have come up with, you know, like 100 is a very common choice. Seems to work okay. It's empirical, for me at least. Yeah, good. Okay, so I wanted to cover just one more thing. Okay, and then I can finish talking about how these neural networks are trained. Okay, so stochastic gradient descent with mini batches, looping over epochs. I guess in Sunghak's tutorials, he will discuss maybe in more detail how all these things work. And in practice, so SGD is what this is called. In practice, people don't use even this vanilla SGD, but they use more advanced versions of it. And 2 popular choices are something called Atom. Another one is called Eta Delta. So when you're actually doing this for real yourselves, you will probably use these instead. And what these are fancier versions of what I just told you. You can think of it as roughly as SGD with adaptive learning rates. So that's what the eta here is, adaptive. So it tries to choose or guess what the best learning rate is based on, it's trying to incorporate second order information. It's trying to incorporate second order information. Yeah, in fact, I probably should have said that. The only difference between gradient, well, okay, no, the Hessian is more than just, okay, if the Hessian were just a one-dimensional thing, this would be just like gradient descent, where the Hessian tells you the optimal learning rate to choose, right? Of course, more complicated than that because this is a matrix, and so it's going to take me off where the gradient is pointing. Never mind that. But so what people try to do with these Atom and Eta Delta that are more state-of-the-art optimizers is they'll try to use the history of where you were. So they'll try to use the history of like the last n gradient updates to get a sense of the curvature. So it's like another way of getting second order information in there. Based on that, they can guess what the best learning rate should be at any given moment and use that. So you'll specify some learning rate, but it'll actually adapt that as it trains. So yeah, so these turn out to be fairly state-of-the-art, I would say. Okay, and the last thing I want to tell you about Okay, I'm way over time. So I think maybe Gregor will have to tell you about overfitting. Okay, thank you. Yeah, sorry. Okay.
After doing the stochastic gradient descent, is there any bad probability from the global minimum to go up to the local minimum?
Right, so, well, okay, so what you'll do when you train one of these things, as you'll see if you go to the tutorial, is you'll monitor the loss, the full loss, I guess. You could if you wanted to. The loss function. So you're trying to minimize this loss function, right? So you'll see the loss is decreasing, 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 decreasing. And if you do jump out of the global minimum or a lower minimum into a higher one, you'll see that because you'll find after some epoch the loss jumps. So by monitoring the loss, you can tell if something like that happened. And then you can fiddle with your learning rate to get a better convergence, or you can even stop. You could say, everything that happened after I jumped, just throw that away. Like where it hit the lowest value, that's my minimum. That's the model that I want. So yeah, so we do things like that. Yeah.
Thank you very much.
Mm-hmm. Question, yeah.
So if you have a fully connected network, it looks to me like there is a very high number of degenerate minima. Because if I swap any two nodes, I don't do anything to the problem. Is this a problem in any way, or do you just want to find one solution and not
Good.
a
Yeah.
unique
So I
solution?
mean, I think short answer is practically it doesn't seem to be a major problem, and yeah, just finding any solution, even if it's related to another solution by symmetry, is enough. Like that's that gives us a function we can use. But I think more generally, yeah, there's a huge gauge invariance or something, or there's a huge symmetry invariance of these things, which I'm not aware. Like I think that's less well explored on the theoretical side, and that's actually some place where, like a lot of physicists I know personally, will quit and go work for Google to study these kind of questions, because they can just keep thinking about fun, conceptual, abstract things and get paid like 4 times more than the rest of us are paid. So, so I think that's something a physicist who understands symmetries and things like that would actually have a lot to offer. And as far as I'm aware, yeah, maybe there's a literature on that, but I'm not deep into that. Yeah, but yeah, there's a lot of symmetries and invariances to even a simple, fully connected network that maybe someday down the line could be leveraged to get an even more efficient fit, I think. Yeah. Any other questions?
Okay, so then why don't we thank Professor Shih again? Yeah. We'll come back at 3:15, I think.